Hi, this is Tom Fitteman at Ventana Systems, and I want to reflect a little more on a post I recently made on MetaSD about the difference between forecasting and prediction, and Forrester's view on the prospects for both, and a few amendments that I would suggest today. And in particular, I want to respond to an interesting question that Samuel Allen raised about how do you actually communicate uncertainty to people. And in doing that, I'm going to use a diagram created by Alan Graham. I'm going to use a simple epidemic model to illustrate what I'm talking about. And I'm using Venity because it makes combining multiple sources of uncertainty and scenario choices easy. But you could obviously do this with any system dynamics software. So the layout here, we have a SIR infection model. We have susceptible, infected, and recovered people, and they're getting infected through contact between the infected people and the susceptibles. And then after some delay given by the disease recovery time, they recover and exit the system. Of course, on the one hand, being recovered sounds like a good thing, but we don't necessarily want to maximize the number of recovered people because that means that we've exposed the maximum number of people to the infection along the way. And if there's any consequence or mortality or misery associated with that, obviously we'd rather avoid it. So probably the real policy variable of interest here is how many people are we able to keep in the susceptible stock at the end of our period of interest. So that's the setup. So this disease or this scenario, we actually called this a scenario entity, is kind of informed by two different kinds of parameters. So there are some parameters that describe the disease, like how many people initially have it, how long does it take to recover, and what's the transmission rate when there's no sort of pharmaceutical or non-pharmaceutical response that would slow things down. And then there are some parameters that describe a policy intervention that we might make. So there's an intervention effect on transmission that's a multiplier on how fast the disease grows. And you can decide when you start, how effective it is, and is there a implementation lag in starting that up. You'll notice that I've laid out two banks of sliders here that capture the parameters for the disease and the ones that describe the policy. So the chart here is showing several combinations that correspond with Alan Graham's diagram, in which you can take a base simulation and then vary a parameter like the disease transmission rate or the disease recovery time to see how the model behavior is sensitive to that parameter. And you can also try the simulation with and without a policy. So you run a base case and then you add a policy and see what the policy impact is. And you could try that again in the perturbed simulations that have a different parameter. So you might combine a policy intervention with some variations in the disease transmission rate in order to discover what Alan calls policy sensitivity, which is essentially when does that policy work or not work, and how is that sensitive to the parameters in the system, which may be uncertain. In fact, they're almost certain to be uncertain. And in this model, why do we have uncertainty? Well, there might be a number of sources. So actually the policy parameters themselves might be uncertain because, for example, policy intervention effectiveness might be unknown. If you're considering, say, mandating wearing masks, there's uncertainty about the physics of that, about how effective they are intrinsically. And then there's also uncertainty about compliance, which might really reflect some missing feedback loops in the model that ought to be fleshed out in a more complete picture of this policy problem. But the other source is uncertainty about the underlying disease characteristics, at least when you have a novel disease coming in. So, for example, back in March 2020, when COVID hit, it was very uncertain what the basic reproduction ratio of the disease was. I mean, it was bounded at, say the early literature said 2.5, but plus or minus 1 or more, which is a big deal for something that characterizes a positive feedback loop. So in this case, if we're sitting at day 40 of this novel disease, we might have some data, which is reflected in these blue circles here, but it might be fairly poor data. And actually, let me turn off the intervention scenarios because we haven't started yet. And more importantly, that data might not discriminate very well between possible alternative trajectories. So the two lines here are different disease characteristics, specifically, if we look at the table here, different transmission rates by plus or minus 10% around a middle value. And it's possible that you could have a higher transmission rate and a lower transmission rate with more people initially infected. That's the red one here. And they have quite different future trajectories, but over the past, if there are any, reasonable sized error bars on these data points at all, you may not be able to tell which world you're in yet. So how do we go about understanding policy sensitivity in this model? It's kind of already shown on this diagram. We've got two base case scenarios with different disease characteristics, and we've got, for each of those, we've got a scenario with and without policy. And now we can start looking at how does the disease or the policy affect things. So, for example, we can take the policy slider here, the intervention effectiveness, and make it greater or less. And actually, you can see sort of some interesting thresholds here where the same policy has a pretty strong effect in one reality for the disease, but takes longer and has a sort of a less immediately noticeable payoff for the more aggressive variant of the disease. So that's one way to do it, but I tend to think there's actually too many lines on the chart here. So one response to that is to simply simplify the case. So I'm just going to turn off one of the two diseases. So now we're just looking at the pure case of we've got a disease and we've got a policy. And now we can vary the policy and see what works. And you can see that this is around 50% effectiveness is a threshold at which the disease is arrested. But if you want it to decline significantly, you have to get substantially beyond that in effectiveness. And if you fall a little bit short, then it continues to grow quite substantially. And actually you end up with kind of cumulative infections being at about the same level eventually, but maybe with sort of intermediate load on the healthcare system being less, which is a good thing. So there's a lot to think about in terms of the dynamics of the disease here as well. So we can also then pick fix the policy, and we can then look at how does that vary as the severity of the disease gets more or less. And you'll notice the axis is rescaling on the chart here. So be a little cautious about that. The peak is no longer as hard. Maybe better to watch the recovered chart. You'll see that we're now doing much better in the policy scenario because we've got the same policy incident on a less aggressive disease. And then if we start increasing the strength of transmission, you'll notice we again cross that threshold where the disease transmission is aggressive enough to survive the policy. And we end up at the same point in terms of how many recovered people there are. But there's some interesting features about this, actually. Even though the cumulative outcome is high, the policy is actually working here in the more aggressive disease. But that's because it's starting at a point that's sort of past the saturation point where you're starting to run out of susceptibles. So a weak policy might be strong enough to have a big influence in the late stages of the disease, but that's not really where you want to have an influence. But the other thing that's happened here is that our disease characteristics are no longer consistent with the data in this run. So we might need to do something like reduce the number of initial infected or adjust the recovery time parameter in order to make the disease fit the data again. And you can actually see that if you switch here. So this highly aggressive scenario actually doesn't fit history, and I'd say even if this were not great data, this would be soundly rejected. So as we go about trying to build some intuition for how policies work in this system, there might be some other ways to slice and dice things. So for example, I could turn on a couple of more variants on the policy that are more and less effective than my baseline. So I'm now looking at a vector of 50%, 40%, and 60% effective. And I can run that. And you can see now I can look at the less effective, the baseline, and the more effective variant of the policy to essentially bracket how effectiveness works. And then I can see, again, where are the thresholds? How does that vary as I change the characteristics of the disease, for example? The kind of logical conclusion of that is to then jump to doing Monte Carlo simulations where we combine lots of policies with lots of random draws of parameters from scenario or from sets of disease characteristics that are consistent with the data that we've observed. So we don't want to necessarily run scenarios that are wildly outside of history or outside of the reality checks that we can think up about, kind of characteristics we'd like to see in the behavior that we're observing. But within the envelope of kind of plausible scenarios, we could do a lot of simulation, which gets you things like this, where you have confidence bounds on the outcome given the distribution of uncertain parameters for the disease and effectiveness of policy. And then you can kind of mine this data to find policies that work hopefully under a wide variety of disease characteristics. And maybe if you can't find a sort of a one-size-fits-all policy, you can take the next step to find a feedback control rule, essentially, that adapts as the changing conditions of the disease reveal themselves. But I think, So these Monte Carlo simulations and stochastic optimization and things like that are kind of the gold standard for extracting information from the model of the system. But I haven't found that presentations like this are necessarily effective with a broad audience at convincing people of what's going on, just because confidence bounds and histograms and things like that may not be readily understood by the audience, and they certainly make it difficult to understand what variation is coming from the policy and what's coming from the uncertain parameters of the environment or the situation. So I think you need a little bit of both. But at the same time, I think there's often the hope that you can essentially get the intuitive insights out of playing around with the model in sort of single simulation mode or simple simulation mode. And then once you have the insight, you throw away the model and implement that. But at least in real world situations I've been involved in, like COVID, the real model is actually more complex than this, because you've got a lot of other things going on, multiple risk groups in the population and vaccinations and things like that. And it's key to get some intuitive insights about, say, the fact that you have to have a policy that's strong enough to arrest transmission in order to get the disease to go back down, and that there will be lags in doing that, policy implementation lags that condition how fast you can respond. But the intuitions alone may not be enough, because presented with a stream of continuously counterintuitive, confusing data, people are likely to backslide. So you want the model around so that you can keep referring back to the data that you're integrating and all of the subject matter expertise baked into the model, and use that as kind of a focal point for bringing all the knowledge together and interpreting the new events in light of what you knew about the structure of the system, and maybe also learning about the structure of the system as you go along. Now, maybe not every situation needs sort of the full uncertainty treatment, but it's pretty common, especially, the bigger the decision, the more of this kind of thinking it deserves. But this is an awful lot for one person to keep in their head, and I think that's why the SUNY Albany folks identified early on that you needed a multifunctional team in a group model building session, for example, to manage all the separate cognitive tasks, because it's very hard to be the modeler and be the process facilitator, and be running the whiteboard and doing all the other things that have to happen in the room at the time the decision's made. And I think the same is true for sort of longer timescale policy interventions, where you need a multifunctional modeling team in order to be sure that you've got your bases covered, that the fundamental model structure is good, that you've got data and calibration under control for informing that, but you're also collecting reality checks and doing extreme conditions tests and checking the units and maintaining the source in GitHub and doing all those things that you need to do to have a quality model. And then finally, you've got to have some kind of process and communication people making sure that you're still answering the question that the stakeholders wanted answered, and delivering the results to them in a way that is comprehensible and appetizing and ultimately actionable. So that's my view of maybe an idealized world of how this should work, but I'd be really interested to hear about how other people tackle these kinds of modeling tasks, particularly with respect to the uncertainty angle, which I think has maybe not been explored as much as it should be in system dynamics. Thanks.